Hello, everyone. So I'm going to be giving a talk about maybe tell me if you can see this, using math in game design. Can everyone read that? All right. Okay, great. And there's many examples of where some surprisingly sophisticated mathematics is useful in designing games. A few examples are there's a game called Spot It. Spot It. Has anyone heard of this game? Well, it's a game that has all of these cards, and it has the surprising property that every pair of cards, so each card has a bunch of symbols on it, and every pair of cards has exactly one symbol in common between the two pairs. So it's kind of a fun game. It's like a pattern recognition game. You just gotta, there's a card, you've got a card, you're looking for which symbol matches, and you're kind of racing the other people that you're playing with. The mathematical connection here is that really what you're doing is that the cards can kind of be analogized to be like lines, and the symbols can kind of be like points in a geometry. So this is a finite geometry, and it's actually an example of something called a finite projective plane. And the fact that every two cards have one symbol in common is like how every two lines intersect in one point, right? So it's kind of cool that there's this very precise analogy between cards and symbols on the one hand versus lines on points on the other. You can make that analogy precise, and this whole game, which is kind of a popular game, is actually just doing some finite geometry, finite projective geometry. Okay, another kind of finite projective geometry game, there's a game called Set. I don't know if any of you have heard of this game, but it corresponds to also some finite geometry, but you're kind of doing linear algebra over a field with two elements in Set. These are not the games that I'm going to concentrate on today. I just want to kind of give you some other avenues, places where surprisingly advanced mathematics is used in game design. The game that I'm going to be focusing on today is a game called Tsuro. So here's the game. It's a pretty fun game, okay? And the way the game works is that there's a bunch of tiles. I'll show you just one of the tiles kind of at random here, and I'll copy it into the talk. So here's one tile, and there's a whole bunch of these tiles, okay? And the way you play the game is you've got a big square, and you and the other players put down tiles one at a time, and you have little meeples, little men, who, if you have a man who's located here, or a person who's located here, they're not gendered, and you put this tile down, then they have to slide along to the other end. So you're kind of putting these tiles, and it's making the people move all across the board as you're creating the board. The goal is just to keep your person alive as long as possible. If they go off the edge of the board, they're dead. Okay, so you're trying to keep yourself alive, and you're trying to send the other people off to their doom. That's how the game is played, right? But what I'm interested in for this talk is the mathematics of the design of this game. So let's look at this piece and kind of think about how these pieces work. So there's squares, and each edge has two marked points on it. And the kind of pathways connecting these points, we always have a pair of points are connected by a path. So if we wanted to build a Tsuro tile, we could do it by kind of just randomly connecting these up in different ways. This would be a valid Tsuro tile. So the kind of interesting combinatorics problem here, combinatorics just means counting. Combinatorics problem is how many tiles are there? And we will see that some interesting mathematics comes into this question, okay? First, let's do this in kind of the most naive way possible. We're not going to get the right answer, but it's going to get us closer to a right answer, okay? So here's a blank square. We're trying to count how many tiles I can build this way. So I'm going to label these points 1, 2, 3, 4, 5, 6, 7, and 8. So, and I'm going to go in order and think about how many options I have. So if I start at point 1, how many options do I have for what 1 could connect to? 7. There are 7 options, right? So I've got 7 options, and no matter what I do, if I do this, or if I do this, or if I do this, or if I do this, I still have some more choices to make, right? So let's say I did this. That was one of my 7 choices. Now I have another choice to make, so I'm going to multiply. How many choices do I have for where 2 can go?
5.
Yeah, 1, 2, 3, 4, 5. It only has 5 places that it can go, interestingly. Let's say that 2 went to 3. Well, now I already used up 3 and I already used up 4, so let's move on to 5. We're just going in order of what's still available and seeing where it should go. How many options does 5 have?
3.
Okay. And then in this case, 6, how many options for it?
1.
Only 1. Okay, so it looks like 7 times 5 times 3 times 1. This already is kind of interesting because it kind of looks like a factorial, but instead of going down by 1 each time, it's going down by 2 each time, okay? This happens often enough that it gets its own symbol, and it's 7 double factorial, which is not the same thing as 7 factorial factorial, unfortunately. Okay, so the 7 double factorial means go down by 2 each time. But if you calculate just 7 times 5 times 3 times 1, you get 105, if I figure rightly. Okay? So what do you think? Is 105 the right number? Probably not, because I'm asking you the question. But is this too many tiles or not enough tiles? If it's too many, give me a thumbs up. If it's not enough, give me a thumbs down. What do you think? We've got kind of a mix here. And if you're not sure, give me a thumb sideways. Like if you really have no basis for answering, just give me a thumb sideways. Okay, a lot of thumbs sideways is 1 thumbs down. Okay, let's talk about it a little more before we make our decision then. So, so we have, I think, really accounted for, you know, if I make a square like this, I label it in this order, then we've counted how many ways there are to draw these paths. I don't think we've made any mistakes there. The issue is that maybe I've counted some things more than once. Can anyone give me, like, what's an example of why I've counted some things more than once here? Yeah? 2 to 3 and 3 to 2. I think we've actually already accounted for that in this counting.
Oh, no.
Yeah.
Because it's symmetrical. So if it's the opposite side, 6 to 7, 7 to 6, right?
7 to 6. Yeah. We could. So basically some symmetry. You said the keyword there, symmetry, right? If I were to take this thing and rotate it, so here I've rotated it, it's the same tile, right? Physically, if I pick this thing up, it's the same thing. But now this was a different thing that I counted. 1, 2, 3, 4, 5, 6, 7, 8. Now 1 is going to 7 instead of 1 going to 4, right? So these are the same tile, but I counted them as different when I did this count. Oh yeah, hand. Was there? It's covered now. Okay. Okay. So how many times do you think? So this is at least twice I counted this tile. How many times do you think that I counted this tile when I should have only counted it once? Hold up fingers. How many times? Seems like 4 times. So I counted this tile 4 times. So maybe we should just do 105 divided by 4. Uh-oh, there's a problem with that, right? That doesn't give me a whole number of tiles. So we're on the right track. We need to account for this kind of symmetry, this overcounting, but it seems like just dividing by 4 is not going to be enough. Okay. Can anyone think of a reason why? So if this did count every tile 4 times, then this would be legit. So obviously something more subtle is happening here. What is happening that not every tile is being counted 4 times? Maybe some tiles are being counted more than 4, or maybe some tiles are being counted less than 4. James?
There could be reflectional symmetries.
Yeah. So if I make a tile that looks like this, okay, let me make a really easy one. Like this, right? Well, so this tile wasn't symmetric at all. So when I rotated it, this was a 90-degree rotation, I got a different one of these things that I counted, right? But when I rotate this guy 90 degrees, I'm getting the same one. I've already counted it, right? So I'm not so this guy's only got counted once. Okay, very interesting. And I forgot, I have some notes. And I will need them eventually because there ends up being some kind of detailed analysis in a bit. Okay, so we need to account for these symmetries. The naive idea was just to divide by 4. But when I divide by 4, this thing should count for 1, but it's only counting as a quarter, right? This thing should have counted for a kind of for a quarter because there's 4 of them. But this guy, I'm counting it as a quarter. It should really count for 1. So let's see if we could make an accurate count that uses the idea of symmetry to see to get that count accurately. Okay. So here's the idea. I'm going to take all 105. I guess I'll distinguish between pictures and tiles, okay? So this thing and this thing, I'm gonna say that they're different pictures, but they're the same tile, okay? So here I've got 105 pictures, but we're not sure how many tiles that is yet. And I'm gonna start with my naive idea. I'm gonna do a quarter of the 105. And let me just imagine that I have some with no symmetries. So then for those ones, I do want to divide by 4. You could think of it like I've got 4 bins. And if I'm going through all of my pictures, if I get a tile that has no symmetry, I'll put 1 here and then I'll look for the other 3 and put them each in one of the bins, right? But then I'm going to have some that are going to have 90-degree symmetry. So I rotate it by 90 degrees and it stays the same, right? I want all of those to count. But the way that I'm going to think about that, because I don't want to, I'm gonna keep this expression going here, okay? The way that I'm going to think about getting these in my formula for the number of tiles is, so if I come across one that has a 90-degree symmetry, so I've got this one tile, it's got a 90-degree symmetry. Well, I don't have 4 of them to put 1 in each bin. I only have 1 of them. So to get an accurate count in each bin, I'm going to have to duplicate this thing, okay? I want to make some extras. So that now I can put 1 of them in each bin, so that when I divide by 4, I've got the right number of tiles, okay? So already, this was all of the pictures. So I already have this as one of the things that I counted in here. I need 3 extras. So I'm going to do 3 times the number that are 90-degree invariant, is what I'll say. After rotating by 90 degrees, they stay the same. Okay? And then there's another type, which is, so something could be, if I rotate something 90 degrees and it stays the same, then if I rotate it 90 degrees again, it's also going to stay the same. So 90 and 90, that's 180. So everything that has 90-degree symmetry has 180-degree symmetry, but not everything that has 180-degree symmetry has 90-degree symmetry, right? You could have something like, you could have something, oh, actually, I've got pictures of them. 180, number 1. Okay, here's one. Clearly, if you take this thing and you rotate it 90, it's not the same picture. But if you rotate it 180, it is the same picture, right? So we also need to deal with the 180-degree symmetries. And for those, so imagine that we find a tile. I'm erasing parts of my notes, so well. But imagine that we've got a tile that has 180-degree symmetry. Like, I'll draw this one. Okay, well, when I'm counting how many of these guys there are, I would want, yeah, basically, since there's two symmetries, I'm going to want to double it because there's going to be this one and there's going to be this one. If I double this and double this, then I've got the 4 that I need. They all correspond to the same tile, right? So I've already got one of these guys in here. I just need to double it. I just need one more. So 180 degree only symmetry. So these are things that have 180, but not 90. So this seems like a good strategy for counting our number of tiles. So the number, to summarize, our number of tiles should be 1/4 of 105, which is all of the tiles, 3 copies of the ones with 90 degree invariance, and 1 extra copy of the ones with 180 degree only invariance. Okay, that is a lot to digest, but I hope at least, even if you don't fully buy all the arguments so far, you can say that spiritually this seems legit. Okay, yeah.
It's just one tile, or is it?
There's lots of them. Yeah, we're not sure how many there are yet. That's going to be, so calculating how many of each type there are is going to be part of solving this problem. Okay, great question. But we could kind of visualize these. So now we know that we've got 105 things total. Some of them have 90 degree invariance. You rotate them 90 and they stay the same. Anything that has 90 degree also has 180. So the 90 degrees are a subset of the 180 degrees, right? One thing is that I want to rewrite this expression. It's kind of nasty to have these 180 onlys. That's talking about this region in the Venn diagram. I've got 3 of these 90 degree ones. So I might as well take one of them and add it to this, right? So if I take one of these 90s and kind of fill in the hole here, right? Fill in this stuff that's missing, then I'll have 1/4 of everything plus twice the 90 degree invariant ones, plus now all of the 180 degree invariant ones, not just the ones that don't have 90 degrees. Does this make sense, how I got from here to here? Okay, cool. I'm going to do one more thing. So this is already great. If we can count how many 90 degree invariant ones there are, and if we can count how many 180 degree invariant ones there are, then we'll be done with the problem. But I want to do one more rewrite of this just because it's cool, okay? I'm going to think of all of them. So all of the pictures are invariant if I do a 0 degree rotation. So I'm going to think of this as being the 0 degree invariance. 90, if something is invariant under rotation by 90, it's also the same. 90 one direction and 90 the other direction are equivalent, right? So instead of thinking of this as 2 90s, I'll think of it as 190 and later on 1 270. And then I've got the 180s here. Okay, so the total number of tiles is 1/4 the number of pictures that are 0 degree invariant plus 90 degree invariant plus 180 degree invariant plus 270 degree invariant. Okay, really, this is aesthetically much more beautiful to me than this formula because this seems more organized. Okay, now what branch of mathematics, does anyone know what branch of mathematics deals with symmetries and thinking about, yeah, group theory. Yeah, so group theory, which you'll learn in math 358, I think is the course number here, deals with symmetry. And here we do have a symmetry group. We've got the symmetry of rotations of the square, right? So our group is the 0 degree, 90 degree, 180 degree, and 270 degree rotations. And this has 4 elements. So this formula generalizes massively in group theory. If I have, these symbols really won't make sense to you, but I'll just write it here. If I have a set of things which are being acted on by a group, and I want to count how many equivalence classes there are. These are like my pictures, and I'm trying to collect them into how many pictures correspond to a given tile. It turns out that the number of elements in my set, which is being acted on by a group, up to equivalence by the group action, is equal to 1 divided by the number of elements in the group. That's the 1/4 right there, okay? Times the sum over all of the group elements. So I've got a 0 degree, a 90 degree, a 180 degree, and a 270 degree. So for each element of the group, I'm summing something. And the thing that I'm summing is the size, the number of elements in the set that are left invariant by the group. That's what this notation means. X to the G is the number of elements left invariant by G. I don't know if, when I teach abstract algebra, I usually don't get to this, but did anyone get this formula when they took it? Yeah?
We covered it.
Okay, but you did some orbit stabilizer kind of stuff. So this thing is called Burnside's lemma. And I can't prove the full thing. I would have to teach you too much group theory to do that. But it's kind of cool to see that we were able to just think about it and get to a special case of Burnside's lemma that applied to this game here. Okay. How am I doing on time? Oh, I'm doing great. Okay. So, so that's kind of where the group theory enters into this problem, is that if you know group theory and you know about group actions and you know Burnside's lemma, then as soon as you start thinking about this problem, you're going to think, oh, I'm trying to count how many tiles there are, but I need to take care of symmetry. So like rotations in this case, this is a place where I'm going to use Burnside's lemma. So one of my friends, who's been a friend of mine since high school, has this game and we still hang out. And he asked me, he was like, I know there's a certain number of tiles here, but is that all of them? And I was like, that's a really good question. We should think about that. And I was like, this is a Burnside lemma problem. And then I took an hour or something and I figured it out. So, and then I didn't play the game for those rounds, right? Because I was out of commission. But the point is that you start to recognize that mathematics, even kind of high level mathematics, pops up everywhere in your life when you start to really get familiar with it and integrate it as a tool that you use. Okay, so, but really, okay, so we're to the point where if we can count how many of these pictures are 90 degree invariant and how many of the pictures are 180 degree invariant, then we'll be done with the counting problem, right? And group theory isn't going to help us there. We've just got to roll up our sleeves, get down to it, and start figuring it out. So, so let's see. Okay, so I'm going to do the 90 degree invariant ones first. And this is just a case analysis. So I'll make a square, a blank one here. And let's think about making 90-degree invariant ones. So the first case, for whatever reason, it's because this and this are antipodes. This is directly opposite this about the center line. I wanted to think about that kind of symmetry first. So the first thing I thought when thinking about counting 90-degree invariant ones is, well, what if this was the first connection that I made? Then what can I do with the rest? Like where is 2 allowed to go? Okay, well, let's think about it. Yeah, let me think. This has got to go. Oh, okay, yeah. So if it is going to be 90-degree invariant, then we already know some other things, right? So if I'm going to take this and rotate it 90 degrees, and it's going to have to look the same. Can anyone tell me something else that also has to connect to something else? Imagine taking this thing and rotating it 90. What has to connect to what? Ty?
2 has to connect to 6.
I don't think 2 necessarily has to connect to 6. That would be as if it were a reflection, but I'm rotating it 90. Yeah.
3 has to connect to 7.
3 has to connect to 7. Yeah. Because when I take this picture and I rotate it, I hate this program sometimes. I take this picture and I rotate it 90 degrees. We see that 3 would have to connect to 7, right? In order for it to be the same picture after I rotate. But so far, I think that's it. We don't know where it goes, so we don't know where 4 goes, 6 goes, or 8 goes, right? So we've got some choices now. It has to look like this, but we're not sure about the rest. Now, let's think about where 2 could go. And we'll just test them. This is, like I said, we're rolling up our sleeves. If 2 were to go to 4, then what would happen after I rotated?
Already in 6's position.
Yeah, 4 would have to go to 6, which means I need both of these paths, and that's not legal. I'm only allowed to connect pairs of things. I can't have 2 to 4, and I can't have 4 connected to both 2 and 6. So this is illegal. I cannot connect 2 to 4. What about two to 6? What else would have to be connected to what else?
You'd have to connect 4 to 8 because 2 would go to 4 position, 6 would go to 8. But if those are both present, they equal each other.
Right. So we get this one, and is this a valid tile?
Mm-hmm.
Yeah, this is legal. We got one. Okay, and then the only other option here, I think, was 2 going to 8. And is that possible? If 2 goes to 8, what has to go to what? After you rotate 90. Yeah, James? 2 and 4 have to go to each other. This is illegal again. Okay, so if 1 is going to connect to 5, we only have 1 valid tile in that case. So out of all this work, we got one valid tile. 1 valid 90-degree invariant tile so far. But now let's say 1 doesn't go to 5. So I'm going to take this and let's investigate what can happen. Okay, so let's say what's ruled out so far. 1 cannot go to 5. Where else can 1 not go? Because it would lead to these kinds of problems.
Cannot go to 8 or 3.
It cannot go to 3, I agree. I think it could go to 8 though. Because if 1 goes to 8, yeah, you could have like this, right? So there's no problem with that. Where else can it not go besides 3 and 5? It cannot go to 7, right? If 1 did go to 7, then we would also imagine rotating 90 degrees, right? And we would end up like this, right? And that's no good. So I can't go to 3, I can't go to 7, I can't go to 5. So let's think about where 1 can go. 1 could go to, well, there's 4 remaining options. Are they all good?
We were to
Let's just try them. So say 1 does go to 2, then what else do we know?
3 would go to 4, 5 would go to 6, and 7 would go to 8.
Is this legal?
Yep.
Legal. Okay, let's say that 1 went to 4, then 2 would go to, or maybe let's do 3 first. Where would 3 go? 3 goes to 6. 2 goes to 7. And 8 goes to 5. This is legal. And that was all determined. There was only one way to draw that tile once I knew 1 went to 4. 1 goes to 6. Rotate 90, what goes to what? 3 goes to 8. Yeah, let's actually rotate this one again to see it happen. When I rotate it 90, 3 ends up going to 8. See? So 3 goes to 8. Rotate 90 again. 2 goes to 5. And 4 goes to 7. Legal. And then we only have 1 choice left. It also works, but let's draw it for completion points. So 1 goes to 8. Oh yeah, we did this one already in an earlier example, but there it is. Okay, so we've got 1, 2, 3, 4 different pictures which are 90-degree invariant. Oh, 4 plus this one. So 5 total. Number of pictures which are 90-degree invariant is 5. Okay, a lot of work for that one. Question, Kai?
Quick question. So all the formulas that we have,
Uh-huh.
the way of rotation, like clockwise and counterclockwise affect it at all?
Yeah, so we're counting the this picture is the same picture if I rotate it any number of times 90 degrees one way and any number of times 90 degrees the other way, right? So in this initial formula that we had here, I'm just going to replace this with the number 5. Okay. In this formula, when I've split it up into the 90 and the 270 for Burnside's lemma, I'd be putting a 5 here and a 5 here, but that's 2 times 5 or 5 plus 5, same deal. Formula is still good either way. Okay, so we've got that this is 105. We've got that these are 5. Now we're just looking for these 180-degree invariant ones. Yeah, but remember that they include the 5 that we already counted. Yeah, so we're going to need to count them, including those 5 that we already counted. So let's do that analysis. Again, this part of it, it's a little nasty. You just got to roll up your sleeves and do it. So let's do some case analysis. I know that this is quick. Okay. So let's do the 180 degree invariant tiles. I'm going to do multiple cases. So case 1, I'm going to look at where no pair of antipodal points, that means directly across from each other through the center of the square, no pair of antipodal points are connected. So in this case, I've got 1, 2, 3, 4, 5, 6, 7, 8. The thing I'm building is 180 degree invariant, so I can use that whenever I want. And I'm saying that no pair of antipodal points is connected. So 1 does not connect to 5, but it could go anywhere else. 1 could go to 2, to 3, to 4, to 6, to 7, to 8, right? So 1 can go to, how many places can 1 go right now? 6, exactly, 6 places, right? It can go to 2, to 3, to 4, to 6, to 7, to 8. All of those are valid. But let's then draw in what happens. Let's do an example. Say 1 goes to 3. Well, if 1 goes to 3 and it's 180 degree invariant, what else do I get? What has to go to what? I wrote
7 to 6.
Yeah, 5 to 7, right? If you rotate this thing around in your mind, you could count spaces, right? It's got to come around. It's got to come halfway around, right? So if I went 1, 2 spots, 1, 2, then starting over here across halfway around, I've got to go 1, 2. So yeah, 5's got to go to 7 if I'm going to have this thing be invariant. So because of the invariance, this is forced on me. So I have even fewer choices here, right? Now, how many options do I have for 2?
2.
Yeah, there's, how do you know only 2?
Because it can't go to 6.
Can't go to 6 because we said no pair of antipodal points. I'm glad, hey, I thought I was going to trip you guys up. Right, so we can't go to that one because of no antipodal points. So I only have 2 options, right? And once I do it, then the rest is forced on me. That's a complete tile. So I've got 12 options in this case. Instead of options, I'll say 12 pictures. Again, distinguishing pictures from tiles. 12 pictures have 180 degree invariance and no antipodal points. Okay, and this might include, in fact, it does include like this one, right? This is one of the things that we counted in this collection of 12. Case 2 is exactly 1 pair of antipodal points. Let's draw the picture for this and think about it. Okay, so we want either 1 connects to 5 or 2 connects to 6, or 3 connects to 7, or 4 connects to 8. Or is that it? Wait, then why am I only getting? Oh, I can't have exactly, right. I can't have exactly one pair, because if I had exactly one pair when I rotate, I get another one. So that never happens. So sorry, exactly one pair is 0. So I'll skip that. I'll skip that case. I'll go to exactly 2 pairs. This is possible, maybe. So now I need to choose 2 pairs of points, which is kind of tough. Let me give you a hint. If I'm going to choose 2 pairs of points, I'm really just choosing 2 from this group, and then the ones that they connect to are determined by the fact that it's antipodal. So I just need to pick 2 points out of 1, 2, 3, 4. How many ways are there to choose 2 points out of a collection with 4 objects?
4 choose 2.
4 choose 2. And that is 12. No, not 12. That's going to be 4 times 3 divided by 2, right? If you use the formula, it's 4 factorial divided by 2 factorial times 2 factorial. So that's 4 times 3 times 2 times 1 divided by 2 times 2. The 2 cancels. 12 divided by 2 is 6. Okay, so once I've chosen 2 of them, say I chose this one and this one, I don't know, then 2 has to go to 6, 3 has to go to 7. And then what can 1 go to? How many choices do I have for 1? Yes, I have 2 choices again, because this is not allowed to be another antipodal point. So there's 2 choices there. So 6 times 2 equals 12. In this case, we can't have exactly 3, because if we've got symmetry, the 3 is going to give me all of them, right? So the last case is all antipodal points connected, and there's only one of those, right? Holy moly, we're almost there. Okay. So one, 2, 3, 4, 5, 6, 7, 8. 1 goes to 5. 2 goes to 6. 3 goes to 7. 4 goes to 8. That's 1 tile. So I've got 12 from case 1, 12 from case 2, 1 from case 3, 25 180-degree invariant pictures, not tiles, pictures all together. So now we can go back to our formula, and the number of tiles is going to be 1/4 of 105 plus 5 for the 90 degrees plus 25 for the 180 degrees plus 5 for the 270 degrees. These 5 are the same as these 5. Okay. And 20 of these are 180 only, and 5 of them are both 180 and 90. Right? Okay, so let's calculate it. That's 1/4 of 35 plus, so that's 140. 1/4 of 140 is 35 tiles. And in fact, if you count the number of tiles in this box, which I should show them to you. There's 36. But the reason there's 36 is because there's also this tile that just has a dragon on it. Our math didn't account for dragon being an option. But the rest of them, there's 35 if you count them up. Okay. Okay, so actually the game that was designed had exactly the right number of tiles to have a unique tile for each possible connection, which means somebody had to do this calculation. Maybe they just did it trial and error, found them all and said, oh, I think I got them all. But, you know, if they wanted to be sure, they would probably have to do something kind of like this. Okay, any questions about this? Pretty interesting, I think. Oh yeah, one more thing I wanted to say, just to put your mind at ease, sort of. So if we think about how much of each type exclusively there would be, so the all pictures, the oh, I'm getting them backwards. The 180 degree invariant pictures and the 90 degree invariant pictures. So we knew that there were 105 of all of the, oh no, what am I trying to say? Say again? Oh yeah, the 270 is the same as the 90. Oh, I want to count how many, yeah. So what I actually did here is I divided these up into piles. And I can show you the piles because I took pictures of all of them. So here's the 5 tiles right here that are all exclusively 90 degree, that have 90 degree and 180 degree symmetry. I'll click on just the first one so you can see an example. So this is one of them that has, that's one of those 5 that we counted, right? That's actually the one with all antipodal points that we counted. There are 10 of them that have exclusively 180 degree symmetry and not the 90 degree symmetry. So like there's one of them, but there are 10. And then there are 20 of the rest. So 20 tiles have no symmetry. 10 have only 180 and 5 have only 90, or well, have 90 and 180 is what I should say. Okay, so and that adds up to 35 like it should. And you could figure these numbers out from the calculations we did as well. Okay, so what could you do with this for a senior project? Well, there are several obvious generalizations of this game that you could design and build and count. So what if you use equilateral triangles instead? This is another group theory problem, counting how many tiles. You could try and understand Burnside's lemma, this, you know, the whole proof, and go through it and do this counting problem instead. You know, maybe the tiles are see-through, so that in addition to the rotations, also if I flipped it over, yeah, so well, it'd kind of be this. That would mean that I would have counted some things as distinct in this count that are actually the same if the tile is see-through. So we could think about Tsuro with see-through tiles. We could think about Tsuro where with more points. What if I've got 3 on each side instead of 2 on each side? We could think about Tsuro with hexagons, which also tile the plane. And we could combine some of these things, you know, like maybe we could do 3 on each side of a hexagon, or 3 on each side of a hexagon, but it's see-through. You know, we probably don't want to get too complicated, but you could actually design some of these games, perform mathematical analysis, figure out exactly how many tiles there are, print them out, and we could play it in math club. See how fun the game is.
And this can all be figured out with the Burnside's lemma.
Yeah, this can all be figured out with this lemma, but it's going to involve similar kinds of nitty-gritty detail analysis. Counting the invariants, there's no magic wand. But the idea of accounting for symmetry when counting is important, utilizes group theory. It's an important part of combinatorics. Okay, that's all I got.